A boat catches fire on the river. A firefighter opens a hose and a horizontal jet of water pounds the hull. The water fights the fire and it pushes the boat away faster and faster. Today we compute that motion completely. The boat's speed as it gains mass and its speed at every instant of time. Along the way, we hit this chapter's best trap. The hose ejects water at alpha kilograms per second, yet the boat does not gain mass at alpha kilograms per second. The gap between those two rates is a chase, and the momentum settles it. Here is the problem. A burning boat of mass m0 sits at rest on the river. A firefighter trains a hose on it, and the water leaves the hose horizontally with speed u, at a constant rate alpha, measured in kilograms per second. The river is frictionless. The jet and the boat both move horizontally, and the gravity plays no role in the horizontal bookkeeping. Every drop that hits the boat stays in the boat. The boat's mass grows only because of the jet, and we neglect whatever the fire burns away. Part A asks us to choose a system, decide whether its momentum is constant, and derive the differential equation for the boat's motion. Last video's rule applies word for word. Pick a system whose mass does not change, the same matter at both snapshots. This is category 3 from 2 videos back. Mass flows in and it brings momentum with it. So take the boat, all the water already aboard at time t, plus the element of water, delta m sub w, that will land on deck during the interval from t to t plus delta t. Call the boat's mass at time t, hull plus the water aboard, m sub b of t moving at speed v. Point the positive x direction along the boat's motion. Now the two momentum diagrams. At time t, the water element delta m sub w flies at speed u, while the boat of mass m sub b moves at v. The momentum is delta m sub w times u plus m sub b times v. At time t plus delta t, the element has landed. One combined body of mass m sub b plus delta m sub w moving at v plus delta v. The frictionless river exerts no horizontal force and the gravity acts only vertically, so there is no external force along x. The x momentum of this system is constant. The two diagrams must total the same, and the limit of the change over delta t is 0. Write that out. 0 equals the limit of m sub b plus delta m sub w times v plus delta v minus the quantity delta m sub w times u plus m sub b times v all over delta t. Expand the product, the m sub b v terms cancel, leaving 4 pieces. M sub b delta v over delta t plus delta m sub w over delta t times v plus delta m sub w delta v over delta t minus delta m sub w over delta t times u. The third piece is second order, a product of two vanishing quantities divided by delta t only once, so it dies in the limit. The remaining ratios become derivatives. Delta v over delta t goes to dv dt, and the delta m sub w over delta t goes to dm sub w dt. The result, 0 equals m sub b dv dt plus dm sub w dt times v minus u. One tidy step remains. The boat's mass is the hull plus the water aboard. M sub b of t equals m0 plus m sub w of t. Differentiate, dm sub b dt equals dm sub w dt. The boat gains mass exactly as fast as water arrives, so the equation of motion reads 0 equals m sub b dv dt plus dm sub b dt times v minus u. There it is, the deciding term from last video, mass rate times relative velocity, and this time it is alive. The water arrives at u, the boat moves at v, and the difference drives the boat. Part B integrated. The equation ties speed to mass, and the time appears only inside the differentials, so we can eliminate it entirely. Move the driving term across. M sub b dv dt equals minus dm sub b dt times v minus u. Cancel the common factor of dt, and group each variable with its own differential. dv over v minus u equals minus dm sub b over m sub b. separation of variables exactly as with the freight cars, every speed factor on the left, every mass factor on the right. Now integrate both sides with matched limits. The boat starts at rest, so the left side runs from v equals 0 up to v of t. The boat starts at mass m0, so the right side runs from m0 up to m sub b of t. The left integral is a natural log. The natural log of v of t minus u over minus u. The right side gives minus the natural log of m sub b of t over m0. Check the arguments before going on. The boat is pushed by water it must catch, so v stays below u. Then v minus u and minus u are both negative, and their ratio is positive. The logs are legitimate. Next, the identity minus the natural log of a ratio is the natural log of the flipped ratio. The right side becomes the natural log of m0 over m sub b of t. Equal logs mean equal arguments, so exponentiate both sides. V of t minus u over minus u equals m0 over m sub b of t. Multiply through by minus u and solve. V of t equals u times 1 minus m0 over m sub b of t. Check it at both ends. At the start, the boat's mass is m0, the fraction is 1, and v is 0. Correct. As water accumulates and m sub b grows, the fraction shrinks and v climbs towards u, but never past it. That ceiling is physics, not an accident of algebra. The jet can push the boat only while it catches the boat. A boat moving at u will keep pace with its own spray, and the water alongside will never land. Speed as a function of mass, with time nowhere in it. Exactly what part B asked for. The answer hides a cleaner statement. Start from v of t equals u times 1 minus m0 over m sub b of t, and multiply both sides by m sub b of t. The left side becomes m sub b v, the right side becomes m sub b minus m0 times u. But m sub b minus m0 is exactly the water taken aboard by time t, which is m sub w of t. So m sub b of t times v of t equals m sub w of t times u. Read it as a sentence. The boat's momentum now equals the momentum its captured water carried when it left the hose. That is momentum conservation in one line, and it had to come out this way. Choose as the system the boat plus all the water that ends up aboard by time t. Every collision between jet and boat is then an internal force. The water slams the deck and slows down. The deck kicks back and the boat speeds up. Equal and opposite, canceling inside the system. And because water that lands stays aboard, no momentum leaks back out of the system afterward. So the system's momentum at time t equals the system's momentum at time 0. At time 0, the boat is at rest, and its future cargo, mass m sub w of t, is flying at speed u. Total momentum, m sub w of t times u. At time t, everything in the system moves together at v. Total momentum, m sub b of t times v of t. Same equation, no integral required. The differential equation, the separation, the logs, all of it collapses into a single conservation statement once the system is chosen well. Keep this check in your pocket. It is the fastest way to validate any accretion result. The problem never asked for speed as a function of time, and there is a reason it stopped short. To bring time in, you need the boat's mass as a function of time, and the tempting shortcut fails. The hose ejects water at a rate alpha, so it seems the boat should gain mass at alpha kilograms per second. It does not. Alpha is the rate at which water leaves the hose. The boat is running away from the jet, so water arrives at the deck more slowly than it left the nozzle. dm sub b dt equals dm sub w dt, but neither equals alpha. To find the true intake rate, describe the jet by its mass per unit length, lambda. First, watch the jet stream past a fixed surface, a cross-section that does not move. In a time delta t, a length u delta t of jet flows through it, carrying mass delta m equals lambda times u delta t. Divide by delta t. The mass rate through a fixed surface is lambda times u. That fixed surface rate is exactly what the hose sets. So alpha equals lambda u, which gives lambda equals alpha over u. Now move the surface onto the boat, the stern where the water lands. Take 2 snapshots at t and at t plus delta t. In that interval, the water in the jet advances a distance, u delta t, but the stern runs forward a distance, v delta t. The jet gains on the boat by only the difference, u minus v times delta t. That closing length is the only stretch of jet actually swallowed. So the mass taken aboard is delta m sub w equals lambda times u minus v times delta t, and with lambda equal to alpha over u, that is alpha over u times u minus v times delta t. Divide by delta t and take the limit. dm sub w dt equals alpha times 1 minus v over u. Check the two extremes. Boat at rest, v is 0, the factor is 1, and the boat fills at the full hose rate alpha. Every bit of jet that arrives lands. Boat moving at u, the factor is 0. The water keeps pace alongside and never catches the deck. In between, the faster the boat runs, the slower it fills. The intake rate is not a setting on the hose, it is the outcome of a chase. Now everything is in place for the time dependence. Two results on the table. The intake rate, dm sub b dt equals alpha times 1 minus v over u, and the speed, v equals u times 1 minus m0 over m sub b. Substitute the second into the first. 1 minus v over u is exactly m0 over m sub b of t. So dm sub b dt equals alpha m0 over m sub b of t. Pause on what that says. As the boat gets heavier, it moves faster, and the faster it moves, the slower it fills. The mass rate falls off as 1 over m sub b. Separate variables once more. M sub b dm sub b equals alpha m0 dt. Integrate the left side from m0 to m sub b of t, and the right side from 0 to t. 1/2 of m sub b of t squared minus m0 squared equals alpha m0 t. Solve for the mass. M sub b of t equals m0 times the square root of 1 plus 2 alpha t over m0. Look at its two regimes. At early times, the boat barely moves and the mass grows at the full rate alpha, as if the boat was standing still. At late times, the mass grows only like the square root of t, because the boat is fleeing its own supply. Finally, feed this mass back into the speed formula. m0 over m sub b of t is 1 over that square root. So v of t equals u times 1 minus 1 over the square root of 1 plus 2 alpha t over m0. At t equals 0, the speed is 0. As t grows, the square root grows without bound, and v creeps toward u, but slowly, at the pace of 1 over the square root of t, precisely because the intake that drives the boat is choked by the boat's own escape. Speed versus mass, mass versus time, speed versus time. The full story from one momentum principle and a well-chosen system. 3 results to carry away. First, the equation of motion. With no external horizontal force, 0 equals m sub b dv dt plus dm sub b dt times v minus u, the mass rate times relative velocity term does all the driving. Second, its integral, v equals u times 1 minus m0 over m sub b, which is really the one-line conservation statement. M sub bv equals m sub wu. The boat owns exactly the momentum its cargo of water flew in with, because a well-chosen system made every splash an internal force. Third, the rate correction. The boat fills at alpha times 1 minus v over u, not at alpha because intake is a chase, and that correction is what turned speed versus mass into mass and speed versus time. Next video, the same idea runs in reverse. Instead of catching mass that arrives carrying momentum, the rocket throws mass backward on purpose and fast, and that recoil is where thrust comes from. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.